Thank you all for coming. My name is Megan Garvin. I'm the Director of Research at the Maryland Center for Continuing Education. It's my honor to introduce Dr. Robert Steele. He serves as the Chair and Professor of the Computer Science Department of Capital Technology University. He holds a PhD in Computer Science. He has authored more than 140 peer-reviewed publications, and he's been patented and successfully commercialized. His extensive experience partnering with industry and teaching and research initiatives. His areas of interest include applied machine learning, mobile information systems, artificial intelligence, and health informatics. So I'll hand it over to you, Dr. Steele.
Well, thank you, Megan, for that great introduction. So I will share my screen. I've got some slides that I will work through, but I'm also going to hopefully make it more of a discussion. I'm very happy to make it more of that modality rather than me just working through some slides. So let me just bring this up. Okay, so hopefully everybody can see that. As per the introduction, the topic is from high school to participation in the jobs boom in artificial intelligence. And, you know, one of the key elements to convey here is the nature of some of the career paths and what should be the preparation for those. But I'm also interested, before starting, what is the background of the audience here? Are we is this a student audience? I don't think it's all students, but is there an audience that are mainly teachers? I don't know if anyone wants to volunteer in that regard.
I think we have a mixture of educators, teachers, both at K to 12 and some higher ed, as well as some industry representatives, looks like.
Okay, great. Well, let's have a look here. So maybe we can skip some of this this introductory area here, although I'd be happy to discuss some of these definitions, but I'll talk about some of the career pathways. And I'm very happy to make it a kind of a research presentation as well, to talk about some of the, I guess, impactful applications that in reality we can get students very early in their career to participate in, interestingly enough, maybe some, as per some of the examples seen by Nora just then. Some types of work doesn't require, can be engaged in fairly early, even where it's not just using small or trivial data sets. So here's an initial point on some of these careers, and there's a breakdown here by like current figures on remunerations. These are all drawn from such sources as Indeed, Glassdoor. I think maybe one of them is from Forbes. I think maybe they're all from those two sources. And you can see obviously that we have a very high demand for these particular roles. Do people know that some of these are obviously very different? Do people know all of these career paths? And I actually think we need to make these names known to our students, even at the high school level. I don't think they're aware of these particular job titles. So has everyone seen all of those job titles, or some of them, or?
Some of them.
So let's start with, Deborah says, all the names. So we've got, machine learning engineer. Obviously, this is, this is somebody who's able to typically use not GUI based, but fairly advanced programmatic techniques and deep neural networks and so forth. But it covers a wide gamut, and maybe interchangeably referred to as an artificial intelligence engineer. Diane originally discussed the possibility of debating or discussing the difference between data science and machine learning engineer. I can give my views on that, but does anyone in this audience, given that we're to be a fairly experienced group, does anyone have a view on what are the distinctions? Tough question, I know, but
Just reminding everyone, when you do want to speak, please unmute.
I see there's some chat questions here as well. So let me just follow up on these. But somebody made this point. My students don't know all of these names and they don't know the roles played by these individuals. A chart would be great. Well, we can certainly discuss them. I mean, yeah, remembering that all of these careers are formative at this point. These are not careers that have been codified and developed over a period of even 20 years. Some of these careers are emerging. What that means is that there's not a firm boundary between some of these. Obviously, data science has a little bit longer, pedigree. It's been around for a while. And data scientists in general, I would say, is the person able to, apply machine learning in general to a given problem and formulate the solution, consider, the nature of the data set being used and what's the appropriate metrics of evaluation and what is the, performance maintenance of the models. The difference between a machine learning engineer and an artificial intelligence engineer and a data scientist is, I would say it's nuanced, but I would say that this particular career path is one where you have a greater technical proficiency. Okay, so it's not necessarily data science per se, but it's being able to use some of the latest and cutting edge deep learning technologies. Again, these are not codified careers. These are just emerging, established and emerging names, very established in the case of data scientists and emerging. If you look at the third one, computer vision engineer. Okay, so according to these salary sources, we're talking even higher remuneration. This is, of course, somebody who focuses particularly on machine learning approaches to computer vision, computer image processing, and prediction. So obviously, some of the key technologies are convolutional neural networks and applications in such things as autonomous vehicles, being able to interpret roadway imagery, or along the lines of the simple example Nora just showed, which is certain facial characteristics recognition, or more specifically facial recognition in general, where you're trying to actually ascertain the identity of a person or confirm the identity. So the key point here is that computer vision engineer and machine learning engineer are, these are basically utilizing similar underlying technologies, but the advanced technologies in this space are not technically trivial. You're not going to be able to produce some sort of production solution via using a GUI interface. Okay, so you're talking about marshalling very large quantities of data, challenging in itself, and then training models which are utilizing very complex infrastructure and involve a lot of expenditure even to train them, and a lot of computational power. So these are all fairly cognate fields, but I think that would be the appropriate distinction. A data engineer, this one has an important distinction. Just catch up on some of these questions here. Somebody asked, what is an enterprise architect? Data science focuses on managing data, while machine learning may be focused on image processing. Well, that answer by Alison, I would definitely not say that a data scientist focuses on managing data per se. Definitely a data scientist is more at the end of model model design, model training, model evaluation, and so forth. But it is the data engineer, if we look at this fifth item here, the data engineer focuses on managing data. Okay, so specifically, marshalling and integrating data. I mean, somebody definitely knows the term data engineer because somebody said they know all of the names, but what proportion of the group already knows data engineer? I don't think it's a not unknown term, but it's certainly not known amongst students, I would say, high school students. How many people?
Yeah, I mean, I think that's fair. Hardly any high school students would know data engineer. They probably know data scientists or machine learning before they knew that one.
Right, and I think that, in fact, I mean, we may be speaking to to the initiate here, but even the machine learning term amongst, if you were to compare it across a group of high school students, maybe they've heard the term machine learning, but it's a little bit rarefied compared with the other careers that they're eyeing to potentially move into, doctor, engineer, and so forth. So even machine learning engineer, I think, is a little bit non-mainstream. Data scientist, I think, is fairly commonly known. But the data engineer is the person who because, as we know, when you want to apply artificial intelligence or machine learning, you can't do it without the data. Okay, without data, we have no machine learning. So it turns out that to do any sort of realistic machine learning, you typically have a large task to be done in terms of aggregating or cleaning or integrating or homogenizing data, a large array of tasks, and also tasks that are very, I would say, computer science related. This involves the ability to obviously use relational databases in a sophisticated way, non-relational, unstructured textual data, data warehousing technologies, APIs, various mechanisms you use to integrate data. Because remember that in any particular organization, that the real challenge is that if you have a conception to build an interesting machine learning model, unfortunately, all of the data that's needed for that model just doesn't have to be sitting in one relational database. What are the critical attributes that may be very important for predictive power? Number one, do you even have a relational database capturing all your data to start with? You may not be having all the requisite data, but certainly it's the norm that we have that data split and spread between multiple data stores, relational, non-relational, and so forth. And so that task of bringing that together, particularly in a way that it's going to support the model building, is certainly non-trivial. It requires a very database and data-oriented skill set. And so as a result, looking at this fifth one here, this has become a recognized separate field, a separate career path. If you were to just at least compare based on numbers, if we were to consider salary to be a measure of demand versus supply, if it's accurate measure, it's equally as high demand as a data scientist. And actually, you can see some recent commentary on this space that says that what we need is more data engineers, not more data scientists, but we need all of them are in very high demand. But certainly, data engineer is a separate field. It's a I don't know. It's possibly a derivative field. It's the need for the data that has driven the recognition and the emergence of this particular career path. So if you're not somebody who's interested in or as interested in the model training and model conception, which is kind of the exciting part, if you are more strong in the mechanics and the technologies of data integration and data storage, then there's a high demand for those people in that particular career path. I mean, there's some observations. I'll get to the other ones as well, of course, but does anyone have some thoughts or questions or input on data engineer? Just have a lot of conversation.
I mean, I would agree with you coming from industry as well. There's a nebulous line among these things, but yeah, I think data engineer is exactly what you described, certainly in my experience. You know, some companies, just for the purpose of standardization, will just call it AI engineer, and they'll actually be doing any one of those other things, but they just have one job title.
Right. This is another key point. I mean, having had some experience in what we call the health informatics space, okay? So health informatics is application of technology into health. You know, there were some efforts to separate even health informatics into multiple subfields, but I'm afraid the workforce demand just does not support specializations where, okay, we're going to hire a clinical health informaticist plus a predictive health informaticist. No. So if you look at the overall employment market, unless you're a very large organization, you can't prepare to hire a dedicated data scientist plus a dedicated, in some cases you can, if you're a large organization, you have whole teams, but somebody who actually has the set of skills spanning both the data integration, aggregation, and the model training is highly desirable. And maybe the market doesn't support, certainly for smaller companies, support their differentiation into separate roles. So, and also I would give my perspective that if you are a data scientist and someone who focuses on model design and model evaluation, you better not be ignorant of the nature of the data, because it's all very well to say hypothetically, we're going to develop a model that's going to predict whether we're wearing masks or whether we're not wearing masks and so forth, but it's completely interconnected with the availability of data. The data availability drives the questions you can ask and the models you can build. And it's not just the attributes available, it's the quantities, the distributions of some of that data. So, you don't want to have a fully, in many cases, you want to have your data scientists have to have a good understanding of all the data engineering aspects. And in some cases, the data engineer will have a very good understanding of of what we're calling the data scientist role, the actual model design and evaluation. So that's a great point from the industry.
It was Tom.
Tom, sorry, I was trying to work out your first name from your screen name there. Thank you. It might have taken me a little while. So that was Alison's comment there. Keith commented, semiconductor material science, solid state physics hits the actual physical hardware of computer chips. So obviously, if you look at this list of career pathways here, the odd man out is semiconductor engineer. So why do I mention it? To move into this field, you should study computer engineering, not computer science or data science. But there's an interesting interplay between those two areas at the moment. So, and I'm sure this has been discussed throughout this event and many other AI-related events, but it is, of course, the hardware speed up, the accelerated computing that's driving the viability of a lot of these complex models at the moment through graphics processing units or GPUs. Additionally, a little input here, and again, the audience may be aware of this, but since the early 2000s, we've been facing a Moore's law headwind of a more serious nature. The ability to speed up the clock speed of processors kind of plateaued around 2005. Traditionally we've extracted this extra computing performance by shrinking the transistor size and increasing the transistor density on semiconductor chips. But we're facing physical physics limits. And so that's already been, that has already been hit. And the subsequent maintenance of Moore's law, which is of course this law, this kind of rule of thumb that we double the processing speed per 18 months, has since the slack has been taken up via multi-core processors. Okay, so basically parallelism, you know, on the motherboard level. Only problem is that not all algorithms and not all problems can be handled in a parallelized problem. So we're facing a real challenge. But what that means is that the movement at the moment to maintain the processing speed growth rate is towards ASIC, application-specific integrated circuits, meaning that we will not so much have a generic processor that can, you know, you can just throw any algorithm at it, any code, and it will just do it twice as fast or so forth. It's more about getting the speed up through making, you know, application-specific integrated circuits. In other words, there will be a closer interconnection between the chip design and the planned use of that chip. Obviously, GPUs are a great example of that. They happen to be very fast at carrying out certain types of, what do we call it? SIMD type processors, you know, single instruction, multiple data, that type of parallelism. You know, they are able to handle processing that relates to individual pixels in a larger image, all in parallel through multiple cores. And that's how we get that speed up. And it turns out that type of processing, that sort of algorithmic support is also matched to what is required to train, for example, deep neural networks. So it becomes highly parallelized. And so you're having specific type of chip that supports a specific type of algorithm. So why do I mention Semiconductor Engineer? Because the interconnection between the code you want to run, say we're going to have more advanced AI algorithms in the future, which we will have, it's going to become an interrelated problem with chip design and already is. Data engineer, we've talked about an enterprise architect. This one is a more traditional term. So this is a term that this is not an emerging role. This is somebody who is like a senior technical individual in a company who is able to evaluate both the software needs, the software architecture that's required, and also combine that with considerations of the hardware infrastructure available to provide an architectural solution for a particular enterprise's overall needs. This is a more traditional role. There's a couple of other questions. What makes a computer vision engineer have a higher median salary? What does he do? From Francisco. So, in terms of what do they do, I mentioned that they basically apply the types of deep neural network architectures that are specifically applicable to image processing. Those architectures are very similar to the deep neural network architectures we use for non-image processing. But again, the overall undertaking there is technically far more challenging. You're dealing with larger data volumes. It's a lot of steps above basic machine learning. So what makes a computer vision engineer have a higher median salary? Yeah, again, I think that you're talking about a level of technical proficiency, some steps above your garden variety data science, if I can use that term, and possibly even above, what you might need in terms of deep neural networks applied to, say, tabular data or other types of more manageable data. So I mean, I hope that kind of answers the question. Beyond that, it might just be, you know, again, it's a salary should be a function of supply and demand. It may just be that there's relatively less graduates and industry people coming out with all of the requisite skills. The skills, I would say, are fairly high end. That's the fundamental driver of the high salary. And that's the fundamental driver of all of these high salaries. It's just that I don't think we just don't have the number of smart, brilliant young people or older people coming out with this full skill set. And that's why, you know, why I guess I'm talking at an event like this. We actually have to make more people and more young people in high school even aware of these opportunities. And so they don't decide to necessarily be a doctor. They can be a doctor if they wish to be, but they know that there is a high demand here. These job titles, most students, high school students, have never heard of, but they're there. And another key point that I'll talk about a little bit in the discussion here is that we can actually get students, even high school students, up to a level of proficiency in these skills far more quickly than we might think. I mean, Nora's example at the start showing that you just upload some images from your camera and train a model, that looks easy. But even to do things that are more a realistic type of problem, I think we can get students coming out of high school and going into their undergraduate degree even who are developing a lot of the requisite skills. So for example, at Capital Technology University, we have some high school students engaged where they have what we call, you know, a research experience while in their senior year of high school. I find it goes very well. And I can tell you that a key insight, if you have a high school student engaging with the university and they have strong coding skills already, we can discuss what strong coding skills mean. They are actually able to contribute to realistic problems, realistic machine learning and AI problems from the get-go. And we're not talking about toy examples. So I don't know, that's a key insight if you ask me. The key insight is that we don't have to have the students go through, you know, all of the years of high school and then graduate from their 4 years of undergraduate and then graduate from their masters and graduate from their PhD. I mean, there'll be a certain number, there'll be a good number that go through that full pipeline, but you know, where a student is capable, they can even start to play in realistic problems late in their high school and certainly within their undergraduate. Again, if they're great students, and if they're not as great as students, there's many easy entry points where they can get an appreciation of these technologies. Let me just finish these questions here. Projections estimate that 65% of current elementary students will work in careers that are not created yet due to rapid technological advancements. Yeah, that's a great point by Megan there, Dr. Garvin. You know, I just gave a talk yesterday. It happened on what we call applied artificial intelligence, or a webinar, and the key takeaway is that while artificial intelligence has not yet, and maybe will not for a long time, achieve what's called artificial general intelligence, it's not going to be an easy task to fully replicate human level intelligence, even though that is the inspiration of the artificial intelligence field. Even though that's not the case, machine learning and artificial intelligence techniques can already far exceed human capability in all sorts of applied tasks. Okay, and I mean, I don't know if I'm stating the obvious here, but I don't think it's fully appreciated. So in my talk yesterday, I gave a couple of examples. One, applying AI techniques to malware detection, which is of course the detection of malicious software, viruses, or whatever they might be, versus benign software. And another one was a prediction of what's called elective admission patient mortality. And you know, if it's applicable in this talk, I'll get back to some of those topics. But the even in an area where we have trained experts, say in the medical field, who trained for many years. How many years? It depends on the doctoral, the particular specialty of the doctor. But they're highly trained. They're very intelligent people, and they can have, for example, many years or decade of experience in their field. A trained artificial intelligence model can far exceed the judgment of a fully trained doctor immediately. So, and that's a bit of a, I mean, I know it's a little controversial statement. Somebody might come in there that's not always true. And that's true. It's not always true, but there are many low-hanging fruit where you can currently train models using AI techniques and ML techniques that can predict things far better than any human can currently or ever will be able to do. So this is a key realization and the theme a little bit of this jobs boom in AI. Many things that are done by trained professionals at the moment will be exceeded, even though we will not probably be able to achieve realistic AGI. Everyone focuses on will the machines take over. I don't think that's really what's on the horizon at all. But again, I gave an analogy in yesterday's talk that in 1903, the Wright brothers took inspiration from the aerofoil in a bird's wing to produce the first powered flight. And then, so logically, if you were to take that kind of AI analogy, that shortly after these flying machines would have replaced birds because we've learned from the inspiration of the bird, and now we'll be able to fully replicate the bird, and the birds would become redundant. So it's just kind of a humorous example, but what we're facing with AI is a similar analogy. Yes, the structures in neural networks are inspired by the neurons and synapses of the brain. We get that's inspired a quite interesting learning system, a learning capability within machines, but it's not necessarily the right conclusion to jump to that this means that fully replicating human intelligence is going to be an easy goal, just like we still can't replicate a bird. But before replicating a bird, we have the Lockheed SR-71 with travels at Mach 5. We have the space shuttle. We recently have the Mars Ingenuity helicopter powered flight on Mars. Even though we will not be able to replicate the actual original inspiration, say the human brain, the applied techniques that derive from that inspiration will already far exceed human capability, just as those type of vehicles, flying vehicles, far exceed a bird, but we still can't replicate a bird exactly. But those devices, those flying devices, so we're going to see that as a big impact. Again, this is something I think is very useful to give these explanations to students. It's very transparent at this point that a lot of professional areas are going to be out-predicted by these techniques, and that will transform a lot of professional careers. So that's, I guess, riffing off of Dr. Calvin's comment there. I think the impact of that is underestimated at this point, and that doesn't mean that we'll be able to replicate human intelligence. It will just be a different angle. David asked if these fields are emerging, what are the base skills or job titles that lead into these fields? So the base skills, and I know there's probably been a lot of discussion of this morning, but the base skills for most of these current roles here are programming skills and database skills. Programming, it should preferably be Python. If it's not Python, it should be R. If it's not Python or R, it should be Java. In my view, there's definitely other options. The base skills from Python, you should learn basic machine learning through something like scikit-learn, and then from there to get into the ability to develop deep neural networks. The most accessible technology, again, is open source and freely available, is Keras. But if you're more if your student's a genius in high school, then they can start using, if they're, and to be able to use it properly, they have to be a very high capability student. They can use directly things like TensorFlow or PyTorch. So these are the kind of technologies, the base skills. So you need to have great programming skills. You need to have, you should have a good understanding of data storage and data manipulation. You get some of that with those programming languages, but of course, there's the concepts around relational databases and SQL, okay? Also, I don't believe that machine learning engineers and data scientists actually need a lot of math, okay? So, I mean, I don't know if there's a controversial statement out there, but I'd love to hear from the math teachers who are going to be up in arms, but, you know, does anyone have a view on that? I know it's controversial, but I can tell you that if you're a strong programmer with strong database knowledge, you're ready to go in terms of applied skills. Not fully. I mean, it needs to be guided activities, but anyone want to care to?
I mean, I agree. In industry, we don't usually, the people that write the models that we use have those knowledge, but the vast majority of people are not doing original models. They're using a convolutional neural network that somebody else developed, right? And then you just have to retrain the last layer of the network to do your specific application. And you don't really need math for that, other than basic, you know, a few basic concepts.
Exactly. And this is the amazing thing. So for example, you know, in our computer science program, probably everyone's computer science program, students have to do Calculus 1 and Calculus 2 as part of the Gen Ed, as part of the ABET requirements, okay? So this is fine. And then they do other more advanced maths. They do things like, you know, linear algebra, numerical analysis. This is all good stuff. But whereas neural networks use calculus in their inner logic in a key way, if you use a neural network, you're not going to be doing a lot of calculus, despite what you might think. Even though neural networks are inherently calculus based, you keep finding partial differentials to back propagate, you know, and update the weights of the neural network, including in convolutional neural networks. You're not going to be doing those calculus equations, and you don't even have to understand them. You know, as an applied machine learning person, you use software libraries. You need to know how to call an API. You need to know how to pass it the correct data types as parameters. You need to know how to receive the correct data types as outputs. And then you need to understand, like, overall, what is the meaning of all of the data you're playing with? What is the meaning? What are the samples that you've used to train it? Is the data set you've used to train it representative of what you imagine you're going to be using it for in deployment? But none of this requires calculus, by the way. And it probably doesn't even require linear algebra, okay? So we have linear algebra in our program. Linear algebra is great because it's all about, you know, matrix operations and matrix multiplication. It's so central to how neural networks work. But you know, you should have that in your curriculum, but without knowing a lot of matrix multiplication, interestingly enough, you can go ahead and train your neural networks. So, I mean, I don't know, I'd be happy to discuss this, but this is actually a key point because just due to historical momentum, we have a lot of math weighting in our curriculum. Sometimes that heavy math weighting acts as a barrier to entry for a lot of bright young students. That I'm not good at maths, I hate maths, I want to study acting or something. And but the funny thing is that they can go into machine learning, applied machine learning particularly, not necessarily the innovative model design. It's not needed for a lot of applied applications. You take an existing model and they're getting more and more sophisticated and apply it to your data set and your problem, you can change the world, and you do not have to. You do not have to build from first principles and you know, partial differentials, the new model. So I don't know if maybe it's obvious to everybody, but this actually shows there's kind of a missed point here of how we can flow bright young students. They don't have to believe that they have to be maths gurus. They don't have to be. They should be software gurus at this point. Will that software interface go to be more GUI based or more, you know, no code or low code? Quite possibly, but at this point, the technical barrier to entry, i.e. the coding and the software, remains very significant. If we look at some examples like, the teachable machine example there, which, there's a no code type of solution, you just show some images. Of course, and the example was to make the point that it's a very nice, accessible demo to show and engage students with. But when you come to build your model in industry, as Tom was mentioning, you're not going to have the option of using a GUI. I would say you're going to have to ask, where's that data stored? Is that in that database, or is that in that 1990s database over there? And how do I bring that together? And oh no, it's missing half of its fields. And you're going to have to do a lot of programming. You have to do a lot of data manipulation, data wrangling, whatever you want to call it. So I don't know. I'm happy to make this a conversation. Does anyone have any comments on the role of math in AI education? Some people may violently disagree with me.
I mean, I agree. It's if you're taking the course in how neural networks learn, you have to learn some basic calculus stuff. Use that stuff. But if you're actually just calling the API, exactly like you said, that's all my team does at Microsoft, right? We're calling someone else's API. They figured it out, and we just know how to interpret the results to see if we get what we need.
Right. The people who came up with these models, they put them out in an academic paper. The academic paper has been cited 20,000 times in 2 years. They're like a massive impact. And if you want to be that person, you should know strong calculus and very, very strong technical underlying computer science. But there's going to be a minority of people who develop those innovative algorithms. It's a great space to be. You're going to be very, very valuable if you can do that. But all of the low-hanging fruit here come from using those models, which are always available through a machine learning library or API call. You just need to know how to call them. So you just need to know object-oriented programming. How do I call a method on a class, an object? And you can get all the results that are interesting to your organization, like how well does this model perform for my data and for the thing that I need to predict for my sector or my industry. So that's an interesting point. Anyone else have and I'm not mean to be confrontational here, but does anyone else have a pro mathematics or feel that this is underemphasizing mathematical skill? Happy to debate it. All right, so in these fields, again, what are the base skills? We talked about that, or job titles that lead into these fields. I believe that you can certainly come out of undergraduate into a data scientist role at this point. And you can probably come out of, if you're very strong, you can probably come out into a machine learning engineer role. I think you should have at least a bachelor's degree in computer science. Does it have to be computer science? It could be data science. There's discussion of whether we should have dedicated degrees. I actually discussed with our industry advisory board recently, should we have a Bachelor of Science in Artificial Intelligence? Okay, and they unanimously told me, no, you better not do that. It's not the right thing to do. Why is that? I mean, probably, maybe some people here think we should do that. It's a possibility. It's certainly a possibility. Obviously, if you make the degree a BS in artificial intelligence, it's more narrow by definition. Also, a lot of the skills you need to do artificial intelligence and machine learning are intertwined with general computer science skills. Programming, you need to be able to program at this point. I believe you'll need to be able to program into the foreseeable future. You need to know data. You need to know all these other concepts of data integration. Yeah, even obviously a certain level of statistics needs to be appreciated as well. I think the base preparation is a bachelor's in computer science if you're at the high school level. And then you can go straight into some of these roles based on your skill level and what you can demonstrate via GitHub or whatever forum that you play in. There's some very interesting public forums in this space. If you can show that you're a great coder on GitHub, most employers, I don't know, Tom, if you agree with this, but most employers will say, well, that looks like the real deal. And this guy is only coming out of undergraduate, but look at what he's built and explained. That's fairly convincing. I don't know.
It's very convincing. Yeah, absolutely.
So there's really, unlike some, for example, in the medical field, you have to go through grade 4 before you get to grade 3 and then grade 2 and grade 1 or opposite order. It's very codified career pathway, one of the great things about computer science is that it's a little bit wider open. If you have the skill and you demonstrate the skill, you can take up the role. So within reason. So, this is my comment here to David's question. Are there any teacher internships in these types of fields that allow teachers to get their feet wet and better understand the different roles? So Alison, in terms of teacher internships, where do you mean where would the internship be hosted? Not sure if Alison's still there.
She commented, in science, we can work in a research lab for the summer, something like that.
Yeah, I think that I'm probably not going to be able to give the best possible answer on this. I'm not sure of the full range of teacher internships. Certainly we very much welcome like high school computer science teachers to work with our university. I would love to work with them on curriculum questions or even applied questions if they want to kind of really get into it themselves. That's a little bit informal. I would imagine that there are, so Deborah maybe has an interesting answer on this. Go ahead.
Sure. At the moment, I think it's just fragmented. It depends with different industries. And unfortunately, it looks like teachers have to find them themselves. There's no one good group like you would find in the Siemens research during the summers and things like that. With computer science, and especially with the different industries and different titles changing, it has become a little difficult to have teachers' internships, but I think it would be very important if some state would take some initiative to do that. I know in Texas, they took an initiative to do that, and they have a program where the teachers through city are able to connect with industries and go for summer internship. But at the moment, I don't think there's one that people can just apply to and go.
Yeah, I think it's not at the point of being codified in that sense, but again, just from my point of view, and maybe this is the case for many other universities as well, we would certainly welcome engagement with teachers and basically there's an ability to get involved directly in research projects at the university level. I actually feel that research projects are a very good demonstrated case to learn the skills, both for students and maybe for teachers. The reason being that you see the end goal. It's not just about learning the Python library. You see that you can predict something that's going to save a patient's life, or and I see that's already being discussed this morning, but it's not just on toy problems. You can actually contribute at a fairly early level, even to really interesting, clearly highly applicable. Okay, so let me just get to it. How do these titles fit within the more traditional roles of developer, senior developer, developer analyst? Again, I don't know, I'd be interested to hear Tom's view on this actually, but the question of how do these fit within the more traditional roles of developer, senior developer, developer analyst? I think there's a hierarchy in industry between these roles, entry-level data scientists and beyond, but yeah. Tom, do you have any view on that?
Yeah, very, very similar. Yeah, I know folks, when data science was becoming a thing, before that was a title people used, there would be someone with a software engineering title or software developer title that would just kind of start doing that stuff, and eventually they call them data scientists. So I think these days it has been a bit more differentiated. So basically, one way to view it is as a data scientist is someone who has programming skills that is more focused in this area of programming, where they're calling APIs to do the machine learning and AI stuff. So yeah, and the good thing from a compensation perspective, if you do go for the data science title, they tend to be more highly compensated because of the scarcity you talked about. So, right. And as you said, you don't have to have much knowledge even to get started in it. You just, maybe a course is enough, or doing a project on your own is enough to get started.
Right. And so, this is there's another key takeaway in terms of high school students. It's incredibly accessible. And I think we can pique the interest of students in just how highly impactful their work can be, even at an undergraduate level. And hopefully that will, and then they're aware of these career paths. And it's like the combination of the fact that they can make a high impact, even as a young person, maybe not in a production sense, but at least conceptually. And then understand through example exactly the skills that they would need if they were to do it in a enterprise scenario. It's a good training. It's a bit like, there's a traditional learning model that maybe hasn't received that much success, which is your problem-based learning. I think it's quite applicable in the case of machine learning and AI, which is you try to solve a problem and show that you have the requisite skills. Partially, you need to be prepared for that. So Megan said it would be helpful for the AI community to work towards an AI pathways tool similar to the cyber career pathways. Okay, that's an interesting, great input. Thanks, Dr. Steele. I asked it to entice ELLs getting into these AI fields after high school. So Francisco, what were you thinking about with that, or maybe that's already the explanation? Tom, as
no, I think you have satisfied my question already, Dr. Steele. Yeah.
Okay, so
Thank you.
Probably
Appreciate it.
An industry person, Tom says, I agree 100% with this list of technologies. Okay, great. So that's all right. The Python technology hierarchy is pretty clear. You could go down the R route. A lot of people do, but I don't know. Again, Tom would have some interesting points on this, but I would say that the reason that Python, it's all about critical mass and snowball effect and feedback effect of a particular language. It's not that only machine learning can be done in Python. It's just that so many cutting edge developers and enterprises are using Python that they think about those tools and then they extend them, including the research community and also and so you get this giant snowball. The libraries are more updated, they're efficient versions of them. Other people know how to use them. There's a skill base around, if I need to, I'm not going to start hiring my machine learning people who with scalar expertise, or I might, but that just a little tiny pool of those. So it's a critical mass exercise. So Python is a great choice. So, and luckily in terms of a high school, Python's the easiest language to learn. So it's a good combination. It's the easiest, most intuitive, as long as you don't write it too concisely, it can become confusing, but it's fairly simple to learn. And then it provides the correct first step to all of those ML libraries. And it's just the ML libraries you have to understand what you're doing with. You don't have to become, that's the key point. What about math for computer science majors like the old math and business students? Well, math, as I mentioned, math is still required by ABET or by middle states, or should I say Maryland Higher Education Commission. There has to be quite a lot of maths. So David, do you mean like, should we get rid of maths for computer science, or?
You were having this conversation about, is math important for computer science?
Right.
And so at the time I was thinking, well, back when I was a business major, we took business calc. We took business calc 1, business calc 2. And while they cover a great amount of the same material covered in, calculus 1 for math majors, it also focused more on the math that I would have needed in finance and business. So wouldn't it make sense to, instead of going deep into, theoretical calculus, pull it back into, a little more of the TensorFlow and that level of math, and create a math for computer science majors?
Right, that's interesting. That's true. I do note that even ABET, the engineering accreditation body, they require you to at least cover calculus. But I believe that calculus for computer science students would still constitute that. I think you're right that the math could be pared down or specialized, even for data scientist purposes or machine learning purposes or computer science in general. What generally happens though is, because we need about 1/3 of the curriculum has to be called general education. and we already have general education courses called Calculus 1, Calculus 2. We just inevitably reuse those modules. It would be slightly better probably to tailor them. But in terms of the logistics of a university, having tailored versions of courses and differentiated curriculum can in itself become, what do you call it, a version control issue.
Scheduling nightmare too.
Sorry?
A scheduling nightmare too.
Yeah, there
Right,
are other
exactly.
states.
Every 3 years.
There are other states and other institutions that are doing this and have been for a few years. In fact, it's still highly debated when we come together at conferences, what should and should not be done. Should it be held in this department or that department, and so forth. And customizing usually means it moves over to the other department.
That's right. And it's an interesting point. There's another kind of complexity of what might happen in a university, but and I'm going to put in a highly biased comment here. So anyone who doesn't want to hear this, close their ears. But I believe that things like machine learning should be taught in a computer science or engineering school versus, say, a statistics school or even a business school. So some people may violently disagree with me, but I believe there's good reasons for that. The key reasons are that to actually do hands-on machine learning, you're going to have good software skills, API skills, and you could get them in business as well. Anyway, that's even more controversial than the comments about math, probably. So, but certainly it can be supported in different colleges potentially. In science, we can, okay, that was that answer. That's wonderful. Thing that you will work with teachers. This is how it starts to form a group that works. Yeah, so this is a follow-up comment from Deborah. And I know a lot of the universities around the state are already interested in this, but I really think this is a great thing to do, to let the students know, to have that exchange between the teachers and the universities. Sometimes universities are going to be aware of certain cutting edge advents better than schools, and that's just the case. But it's an opportunity to basically let students know about these concepts. We've only got into one slide so far, so we're not making much progress, but even these concepts are quite convincing, I think, for students. But the big picture is that this idea of applied artificial intelligence, we can already predict better than humans in almost any sector. If you look at the questions of like doing language translation, image processing, these are some of the very hardest machine learning tasks because they're very tailored to the human capability. We just happen to like look around by seeing a little visible electromagnetic radiation reflected off of objects. It's a very obscure way to move around.
So we are going to be yanked back to the other room in about 10 seconds. So thank you,
Okay.
Dr. Steele, so much. And if you have more questions, I'm sure we can get them to him.